Well, good afternoon, everyone. My name is Brad Bradshaw. I'm president of the Hydrogen Energy Center, and I'd like to welcome you to the second series on hydrogen. And this week we'll be talking about long-term hydrogen storage and some of the specifics associated with approaches that people are taking with that form of storage. And what we're talking about here certainly is.
I know that there's another way of doing that. I know there is. Well, you can talk with me.
I'm telling you that is. Well, we've got the the mute situation going on again. If everybody could mute their microphones,
I gotta do this first. I don't care about that.
That would be appreciated, and we'll see. Try to see who's not muted.
We can't do it. Then it's a separate thing.
Brad, you may have a switch on your screen that allows you to mute everybody at once. I'm not sure about that, but you might take a look.
Right. If you're meeting, you can mute all. Howard.
Okay. Thank you for that advice. We have now muted everybody, and everybody has the opportunity to unmute themselves should the situation arise, which would be fantastic. We have a presentation material with some introductory information about the Hydrogen Energy Center and Valerity, who are the sponsors of today's session. And we are available to answer any questions you might have after the session. We certainly will entertain as many questions as we can get to on this topic, which again is another whole universe of information out there that's I'm sure new to many of you. So we'll use the I think it's the chat box, which I don't see on my machine. Yes, but please use the chat box for questions, and don't be afraid to enter questions as they pop into your mind during the presentation, and we will review them afterwards as well. So we will share the presentation. Can everybody, Dick, or Rick or Doug, can you see the presentation?
Yes, I can, Brad. Thank you.
Super. So this topic is long duration energy storage with hydrogen. And the agenda for today is to provide a very brief introduction to the Hydrogen Energy Center, Valerity, and then we'll look at some key elements associated with these developments. One being the hydrogen drivers. Why is hydrogen new now, whereas we've gone through several hydrogen hype cycles? We seem to be in a third major hype cycle, and people are wondering, is it going to stick this time? And so we're going to look at some of the fundamental changes that have occurred that make this time different. We're going to look at a few of the technologies of long duration energy storage. Hydrogen is just one of many options that are available. And we're going to then look at the specifics associated with how to store hydrogen for longer duration. And we're going to spend a certain amount of the back end of the presentation on geologic hydrogen storage. The reason for the focus on geologic is the scale. Hydrogen is not so efficient, as you all know, from a round trip efficiency perspective, but the scale opportunity to do seasonal energy storage is phenomenal. So when you store a huge amount of hydrogen, for example, in a salt dome, you are able to amortize the capital cost of that storage system development capitalization over many, many kilograms, many kilowatt hours. And that's where the play comes into focus. And then we'll look at some of the hydrogen energy storage projects that are being proposed around the world. And we will focus on the Intermountain project in Delta, Utah, as a specific case. The Hydrogen Energy Center was founded perhaps 25 years ago, and it has always been focused on the use of hydrogen as an enabler of a renewable energy future. It seems as though the world is catching up with the Hydrogen Energy Center finally. We conduct forums, we've done research, and we're really all just focused on helping people understand what hydrogen is and what it means, and what the business opportunities are around hydrogen. We also have actually done project work and research work in the hydrogen field. We'd like you to consider being a member of the Hydrogen Energy Center. It's only $50 a year, and it supports our activities to spread the word on hydrogen and engage in projects regarding hydrogen as well. In fact, some of the work that we've done is come out through these forums. We did a project to investigate hydrogen energy storage on islands, and found that there is a hybrid solution that makes economic sense for hydrogen storage with lithium-ion batteries on islanded grids. The upcoming hydrogen sessions, next week, we're going to be looking at long-haul trucking, which has a significant upswell of investment and interest around the world. There are some remarkable developments. Hyzon Motors is one of the key companies to watch in this space. They're building a manufacturing facility in New York State for their trucking solution. And they're building a fuel cell manufacturing facility in the Chicago area to support, I think it's 100,000 trucks being manufactured per year. And they actually have trucks deployed in Austria and New Zealand at this time, and perhaps Switzerland and some other places. The May 14th, in 2 weeks, we're going to be looking at 100% hydrogen in pipelines, and this is a long-term vision for some of the natural gas companies to not only integrate hydrogen into their existing natural gas mix, but to ultimately develop 100% hydrogen pipelines, and some very interesting prospects being developed in that area. So we will keep you informed as to what the sessions are going forward. Valerity is a research consulting firm that helps companies understand market opportunities, develop new businesses, and source capital. We are doing some work now in the gas field with the transition to renewable natural gas and hydrogen to decarbonize gas grids. And we've also done significant work with equipment manufacturers on business planning and raising capital and finding markets, etc. The illustrative clients that Valerity has had over the year runs the range of electric companies, equipment manufacturers, network operators, both electric and gas on the energy side, full range of projects. So today I want to start the presentation on the long duration hydrogen storage. The definition of long duration is maybe a little squishy, but sometimes the word is used seasonal storage with hydrogen, with the idea of being able to store renewable energy during the summer and being able to produce electricity in the winter, and the idea of having, long duration, 6-month duration storage with hydrogen. So we're definitely looking at more than a week, more than a month, potentially up to 6 months. And so that's somewhat of the definition we're working with here. And we'll talk about why this is the case. But first, let's begin to talk about what are the dynamics that are making hydrogen viable today. One is the changing grid economics with the must-run, zero marginal cost renewables displacing coal and gas plants today, and the challenges that the variable renewable energy has for grid operators to maintain a reliable grid. And hence we're seeing the introduction of battery systems to help first with the 15-minute power requirements, and now batteries are being used for up to 6 hours of storage. It's important to recognize that we have a lot of focus on lithium ion in this world, but over 90% of the energy storage on the grid today is pumped hydro, which has been a significant contributor to intraday arbitrage on the grid and maintaining a reliable grid. In fact, pumped hydro was originally developed to provide grid support in the event of a nuclear power plant going offline. When you have a 2,000 megawatt nuclear power plant and it goes offline in a minute, the grid really needs a lot of support in order to maintain reliability. And that's why pumped hydro was mainly developed in the 1960s to support reliable grid. The zero carbon targets are requiring new approaches to grid planning. And a lot of a lot of the work is focused on increasing the proportion of renewables on the grid, and then the addition of storage. And the question comes: could we operate a grid without any fossil fuels from a dispatching capability perspective, and just have 100% renewables with energy storage? And if you run the numbers on the cost of a lithium-ion battery to provide multi-day or multi-week storage, the economics just don't work. And so the question is, what is it that can be done to improve the economics of long-duration storage in order to have a grid that is just renewables and just storage? There are solutions that we might discuss in a future session, which is the production of fuels from hydrogen and carbon dioxide, not just methane, but there's also ammonia and methanol that are sometimes run in these calculations to determine, can we use a liquid fuel solution as storage? And that is something that should be looked at. We're not looking at it today as well, but it's important to recognize that these other options are out there. And then hydrogen has emerged as a potential solution in the long duration storage gambit, and the idea of moving to a zero carbon grid. And the hydrogen production costs have really cratered with the variable renewable energy, with the curtailment and oversupply circumstances. And the question is that a viable pathway to take? And a lot of the companies that are involved in the gas industry, and more so on the manufacture of gas turbines, have already introduced turbines that are hydrogen ready up to a point, from 10% to 20% to 50%. In some cases, they can take in a mix of hydrogen with natural gas already, and future developments are underway with that. It is important to point out that some of that might need to be combined with ways to mitigate the NOx emissions associated with hydrogen production, hydrogen combustion in turbines. So let's look at what's going on in the renewable energy space. The first is this is the growth in renewable energy in the United States, and you can see that it continues on an upswing, and the expectation is that it will even accelerate more as the costs have come down and the interest in decarbonizing transportation and heat energy is increasing the burden on the electric grid and the need to even accelerate the development of renewable energy. It would be a crime if it would be an interesting circumstance, not a crime, an interesting circumstance if the electrification actually proceeded faster than the deployment of renewable energy, such that it would increase the amount of fossil fuel production on the grid. But that's a question for another day. What is the impact of this growth in renewables? Here we can see a sort of a combo chart. It includes the California ISO and the ERCOT in Texas. So those are the two grid operators, one for California, the other one for Texas. And they publish reports which show the amount of solar curtailment every month on their system. And we've also included the best fit linear. Texas has really come out of the box. I mean, they took a while to get their solar regulations properly situated, but you can see that the incredible growth in solar in the last 4 years in Texas has also been accompanied by an extreme level of curtailment. The curtailment level in Texas is upwards of 6% of the output of the total solar that's going on. And you can imagine that there's some consternation in the project developers who maybe didn't see that 6% of their production would be shut off every year. And this is a concern. Now, California, the growth line looks rather demure in comparison. You can see Texas really came out of the box hot and fast, and it's probably much more subdued growth in the curtailment now. California has been growing 50% per year in curtailment, which is significant. They're upwards of 1.5 million megawatt hours a year, which is enough electricity for 300,000 homes. And that's electricity that's just flat out being curtailed, shut off, because the grid doesn't need it. It can be locational in terms of constraints, but it also can be a demand supply mismatch as well, which is key here. So it really begs the question, well, what's going to happen in 10 years when we have 3 times the wind and 3 times the solar on the grid? The long-term trend is really incredible. This is a graph of all the utility scale projects in the United States for solar and the associated PPA prices. And this is in dollars per megawatt hour. And you can see that the best fit is down around 2.5 cents per kilowatt hour here in the United States. With a range of projects over time. The bubbles, by the way, are the size of the projects. So this trend is it did sort of flatten and maybe go up a little bit in 2019, 2020. So there are some supply constraints that can drive prices upwards in these systems, but it generally is hitting new lows every year as we go forward. On the international front, this pertains to perhaps a future session as well when we talk about international hydrogen markets and the ways in which hydrogen is being converted to ammonia and then shipped around the world in that form. And those projects, the biggest one is a $9 billion project in Saudi Arabia. And you can see here that Saudi Arabia is down at a penny a kilowatt hour for solar PPA. And it helps to have, low-cost land and lots of sunlight, and that coupled with very efficient deployment strategies and very low-cost panels. And we have a circumstance there at a penny a kilowatt hour, that the cost of hydrogen is only 50 cents a kilogram at that point. So you can see why they're going to join in with electrolyzers and produce hydrogen, and then convert that hydrogen to some means to enter and develop the global market. And just for contrast, I use the kilogram a lot in hydrogen, mostly because the kilogram is what's used to measure hydrogen in transportation. And if you go to a fill-up station in California right now for hydrogen, it costs between $14 and $16 per kilogram, which is a bit much. There have been 2 developments in North America that have brought that cost down to about between $10 and $11 per kilogram at the fueling station from a retail perspective. But it's still a long way from 50 cents to get to $10. But this is part of the direction that it's going. Next week, when we have a discussion on the trucking industry, we'll bring up the Plug Power, for example, is working with a major renewable energy company. And I think they're going to be putting in a very large renewable energy system in Texas to produce liquid hydrogen. And the reason is that there's good insulation, low-cost land, and they can put in a big system that has a low cost. I did point out that there is a system in New Mexico which came out at 1.5 cents a kilowatt hour. And so all of these sites on the global stage, it's not just Saudi Arabia, the Arabian Peninsula. There are other locations in the world where these competitive prices are coming out as well. And I think India has recently announced close to a penny per kilowatt hour. So this is the fundamental transition that is driving the interest in hydrogen. Now, from an economic perspective, this is a graph of the hourly prices over a 2-week period in Denmark last year. It's a price duration curve, and you can see on the left side of the chart that the day-ahead price, dollars per megawatt hour, is below 0 and close to 0 for a certain amount of the time, for about 15% of the time, it's less than a penny per kilowatt hour, which is really remarkable. And this is what's going to drive the opportunity for hydrogen as well, especially in the storage, which is the opportunity to do arbitrage between the low-cost hours and the high-cost hours as we go forward. And it is expected that this type of chart will be replicated, and the left side of the chart will go down and the right side of the chart will go up the more renewable energy we have on the grid. In other words, the arbitrage gap, the differential in price is going to only increase as we go forward. Historically, in the last 30 years, I've looked at these numbers, and the grid has been very efficient at reducing the gap between low price hours and high price hours. And what we're seeing with renewable energy is that is reversing. We're going to see a dampening of the low price hours and an increasing price in the high price hours. So now we're going to switch to talking about the long duration storage. And here I just want to mention that there are a number of technologies which are available and are being pursued aggressively. Flow batteries have been around for some time, and they they've always had sort of interest, but some of the companies have had a difficult time in the last few years. They remain expensive, but the potential remains high, and so investment continues to go into the flow battery area. I'm somewhat bullish on flow batteries myself. I think there is a shoulder time that is in the 12 to 24 hour period that flow batteries are going to have a important role to play. Pumped hydro remains a lot of interest in developing it, but it has significant challenges in location. It certainly has an environmental impact. Frequently you find a place with a mountain that you can put a reservoir near the top of a mountain above a river, and then you basically pump up to the mountaintop and then run it back down. The economics are well developed there, but it's very difficult to locate and develop pumped hydro sites. Hydrogen, today's discussion. Stacked blocks is another. There's a demo, I think it just started up a few weeks ago, which is concrete blocks are being elevated with a crane and stacked. And that's the energy storage. And every time you raise it, it takes energy in. And every time you take a block off the stack and let it, run back down to the ground, you're producing energy. And we'll see how that goes. It has the advantage that the electric motor generators that are used are fairly efficient for the round trip efficiency. Liquid Air is another company that is developing a thermal storage solution. There are other thermal energy storage solutions that are out there of scale, and the idea being is you use the heat to then run turbines either through steam or hot air. These systems were originally developed in the solar energy field with the concentrating solar energy systems to store energy so that they can be a dispatchable overnight resource. The CAES is compressed air energy storage, and compressed air energy storage, there are two plants, one in Germany and one in Georgia. And it's been an opportunity for years, but it's never really developed because of the economics. It's an interesting twist. CAES is usually done in a hybrid situation where you compress air and you release that air, and you do capture the energy from the pressure differential, but you also mix the air with natural gas and then run the combined air natural gas mixture through a turbine to generate electricity. So it's usually done in a hybrid design. And that's interesting here because a lot of the hydrogen plants that are being considered are initially being done in a hybrid circumstance with natural gas as well. Today's discussion is really not focused on all these other technologies. That would be a whole nother, each one of them would be a whole nother session. So I apologize if there's brevity in looking at these, but I do want to recognize that it's quite a horse race going on for the long duration storage. One way that simplifies an understanding of the different technologies for longer duration is to look at this chart, which looks on the horizontal axis at the storage capacity of these systems, and then the vertical axis being the discharge time of these systems. And if you believe the numbers that go into these analyses, and there are many different ways that people have presented this information with different technologies. But you can see flywheels indeed are used for very short burst needs for grid support, etc. And then you can see batteries going up to about, in this case, they're just going up to 8 hours, and in the next 10 years, batteries are definitely going to go up to, 10 to 16 hours easily in terms of the applications. Then we see compressed air pump storage, but then, power to gas and hydrogen, power to gas methane being much longer discharge times and much higher quantities of storage capacity. Scale is a critical issue when you look at the entire grid of the United States and the amount of energy that we're going to need to store if we're going to go to a renewable plus storage basis. So in the oversimplification category, we have a diagram of the long duration hydrogen storage approach. You electrolyze water to produce green hydrogen using renewable electricity on the left side of this chart. You dry it to make sure there's no moisture, and then you compress it and inject it in a salt cavern in this case. There are other storage media, and I will show you those in a minute. The current approach is to mix the hydrogen with methane and run it through a combined cycle gas turbine, which is about 61% efficient in its output, and produce electricity. Fairly straightforward. The technologies that are used in these systems are well established. I think the electrolyzer world is going through a several hundred percent growth in the next few years, depending on the different markets that expect significant electrolyzer deployments. Major ones, Nel, ITM Power, Cummins, and Plug Power, which acquired several electrolyzer assets in the last few years. Historically, they were not in the business, but they have entered it in the last 2 years. And then in the turbine business, GE, Siemens, Hitachi Power, Mitsubishi Power, that's a misspell. It used to be Mitsubishi Hitachi, and Mitsubishi bought out Hitachi's share last year, so I apologize for the error in the labeling here. It should be Mitsubishi Power. And they all have hydrogen-ready turbines available today that they're putting in. The storage approach to bulk hydrogen storage, there are more. There's a buried pipe approach, for example, where you take you take certain pipes and bury them. I'm not sure you'd want to use steel, but I suppose you can. But I do want to point out these 4 approaches. One is the spherical pressure vessel. Then there's spherical cryogenic. There's an approach called the lined rock cavern, which is fascinating. And then there's salt dome. Now, if you look at these are all based on pretty much sort of the larger projects that are out there. And so if you're looking at scale, this is not the average or the minimum. This is really more towards the maximum, as it turns out. So a spherical pressure vessel, you can store 23,000 kilograms of hydrogen at 10 bar. The cryogenic, the one that's pictured, is a liquid hydrogen storage in Japan that takes in liquid hydrogen from Australia. That's 177,000 kilograms. NASA has one of the biggest storage vessels in the United States, certainly for the space program. Then we go to a lined rock cavern, which is kind of unique in Sweden. It really is a heavy lift approach. You actually go down and you build the cavern yourself, and then you line it with a steel lining, and then you may put additional plastic liner on that steel in order to keep the hydrogen in the system. That one you can see is 650,000 kilograms. I also only mention that because in the Northeast United States, where some of us reside, there aren't really any salt caverns, but there are rock caverns that can be used for bulk hydrogen storage. So in cases where salt domes aren't available, a lined rock cavern is an approach that can be taken. And then you go to a salt dome, and this is a salt dome that's used to store hydrogen in Texas that's owned by Praxair. There are 3 pre-existing hydrogen storage facilities, underground hydrogen storage facilities in the United States, and this is one of them. And you can see that that stores 4 million kilograms. And also want to point out that in some of these cases present the total kilograms and then the net kilograms, and that's because there's residual hydrogen that's in the storage medium that you don't have access to. For example, in a salt dome, there's a minimum pressure requirement that you don't want to go below, because then the dome might change shape, and you'd then be in a situation where you might have leakage. So in this particular case, it can be 40% by volume, which is called the cushion gas that's used in these salt domes. So just, the calculation for storage is perhaps not as straightforward as you might imagine, but the numbers are fairly straightforward in terms of the cushion gas that's required to maintain the structural integrity of the salt dome. Now, the hydrogen storage that Praxair has in Texas, it's used to ensure their supply of hydrogen to a 310-kilometer hydrogen pipeline that runs along the Gulf Coast from Louisiana to Texas, through Texas, and it's just part of their delivery infrastructure for hydrogen in the petrochemical field. Another thing about salt domes is basically a salt dome is just that. It's a formation of salt underground, and when it's developed for hydrogen storage, you don't use the whole dome, you just develop a part of it. In fact, we're going to be talking about the IPP project in Delta, Utah. They envision they're above a single salt dome that they think will be able to hold 100 caverns for hydrogen storage. On the left, we can see a depiction of the process, and it takes time to develop these sites. But basically, you drill a borehole down, and then you flush water into the salt dome, and that water turns into a brine at which you pump out. And in fact, one of the costs of developing these facilities is the cost to transport the brine away from the salt dome by truck, and then to dispose of that brine in an environmentally responsible fashion. The geologic formations associated with salt are well known throughout the world. In the United States, you can see we have readily available quite a number of areas which have salt deposits, which could be used for salt dome storage for hydrogen. In the UK, it's the same situation. I apologize, it's hard to see, but the labels on the graph, the labels on the map all point to distinct salt deposits that could be used for storage. And in fact, the UK has 27 sites in these areas being used for natural gas, but there are also other gases that are used, as well as mixed gas situations. City gas has been put in with 97% hydrogen. There are other mixes with 50% hydrogen and other gases as well. So there's quite a industry expertise already established in terms of being able to find and develop and use salt caverns for gaseous storage, and hydrogen is just another gas that can be applied. This is some detail available on the pre-existing facilities that store hydrogen. You can see the geometrical volume of these sites. The Praxair, 566,000 cubic meters, and then the Spindletop is close to 1 million cubic meters in volume, fairly significant. This is the reality, which is hydrogen has been a industrial gas for 100 years, and there's a lot of experience with using it and storing it around the world. There are quite a few projects being proposed and in develop and in pilot phase around the world. Today, I'm just going to jump right over and talk about the Intermountain Power project, and then we'll have some time for question and answer on this. And this presentation will be available, so you'll be able to dig into any of the details as you like as well. So one of the most significant hydrogen energy storage projects is the Intermountain Power project in Delta, Utah, which is a $1.9 billion project. And Mitsubishi Power is a major entity that is going forward with this, and they all have a part that's separate from the power plant per se. But the core driver, which isn't identified here, the core driver is LADWP, the Los Angeles Department of Water and Power, has an objective to be carbon-free by 2045 in California. And to reach their 2045 zero carbon goal, they took a look at this power plant, which supplies quite a bit of electricity for LA. There are many partners in this plant, but LADWP is the major one. And it currently is 1,800 megawatts, and it's coal. And it's pretty obvious what's happening in the coal industry around the world is that that's going to be retired by 2025. They're going to replace it with a smaller power plant, less, half the size. And it's going to be basically a natural gas combined cycle power plant. They're looking initially at a 68% capacity factor, and they're requiring hydrogen-ready turbines so that they can feed up to 20% hydrogen to begin with from day one. And they expect to commission this new facility on the same site in July of 2025. Now, the next phase, it's not exactly clear how all these different phases are going to interact, but there's a couple of objectives that they're trying to reach. And one is certainly to be zero carbon by 2045, and then to gradually increase the amount of hydrogen to be 100% hydrogen. And they say in their materials by 2040, and I think they made a mistake. I think they mean 100% hydrogen by 2045. They're also including a 160 megawatt compressed air energy storage system, and they expect that system to be converted to hydrogen. So it'll be a compressed air energy storage to begin with, and then they'll convert it at some point to a compressed hydrogen energy storage system. And they also considered that there's room for 100 caverns in the salt dome in Delta, Utah. And so one can imagine they'll keep the compressed air energy storage, and then they'll add another dome, which will be the first hydrogen dome as they go forward. The area in which they're located in Utah is a confluence of major transmission systems that are connected to significant wind power systems, and the queue for interconnection with solar is tremendously large as well as additional wind. So they see that entire Utah area as being a real foundational place for significant amount of renewable energy, and this is part of the driver in being able to put in a large storage system here, in that they see that there will be these times during the year where the cost of the electricity will be below zero, at zero, or near zero as they go forward. So it's a very large energy arbitrage opportunity. Now, I'm just going to go over some numbers here, and I apologize. It perhaps is there's quite a bit of numerology in one fell swoop, but I think it's always helpful to understand some of where these numbers are going. The estimated cavern for the IPP project, and they put it in barrels, so 4 million barrels. What that correlates to is 4.5 million kilograms of hydrogen, net hydrogen, usable hydrogen in each cavern. And you can see that they could put 100 caverns, they estimate, in that salt dome. Now, in a minute, we'll understand why that number is just way too big for their need, or they're going to need to expand, back over 1,800 megawatts in terms of production. So for the 840 megawatt combined cycle turbines at 68% capacity, they would produce 5 million megawatt hours a year. And if you did this on a full annual basis and stored all the hydrogen, this would require 53 caverns of hydrogen, 246, basically 250 million kilograms of stored hydrogen. Now, in reality, if they go to 100% hydrogen and they're using the turbines at 68% capacity factor, indeed they would need, 53 caverns of stored hydrogen. But certainly that's not really what's going to happen. The storage of hydrogen will be used perhaps on a monthly basis. It could be stored for a month, it could be stored for 3 months, it could be stored for 6 months. But it also begins to tell us that in truth, if this is a facility that is really just stored energy and not energy production, they actually are putting in place a contract for natural gas that runs to 2045, which means that they're going to be running this facility on natural gas for the life of the facility. But 100% hydrogen means it's really just a storage facility, and they'll probably only use it 40% of the time in terms of production, and 40% of the time in terms of injecting hydrogen in the storage facility. So they won't get a 68% capacity factor if it's pure storage. It would be quite a bit less, certainly less than 50%, probably less than 40% in terms of a utilization factor. In terms of the numbers, producing hydrogen with electrolysis at 2-cent power, so let's assume that there's significant curtailment, that there's significant zero-cost power, and 2-cent power and 4-cent power. Basically, it results in a cost of hydrogen of about $1 a kilogram with 2-cent power. Now, to convert that hydrogen back into electricity, assuming the efficiency of 61% in a combined cycle gas turbine, which is the efficiency of a turbine that is available for this purpose, it would be 20 kilowatt hours produced per kilogram, resulting in a marginal cost of power of about 5 cents per kilowatt hour. So you can see this is all about the arbitrage. Can they procure electricity for 2 cents or less? Can they sell that electricity for 5 cents or more? And that really is the point here. And they have an expectation that indeed that will be the case going forward. But you can see that spread, this is all marginal cost data. You need to certainly include some additional analyses to look at the levelized cost of energy here. But certainly when you're looking at marginal costs, you have to be below the 2 cents or above the 5 cents in order to make this even viable from a starting point, and then see how your capital recovery ratios are going as you go forward. So their expectation has to be that they can get 2 cent power in, and maybe something on the 7 cents to 8 cents in terms of the sale of that electricity back down to LADWP on a going forward basis. So I know that's lots of information that we've covered, but I did want to leave a little time for question and answer as we go forward. Doug or Rick, do you see any questions that we need to address? And remember to unmute.
Can you see?
Brad? Yeah.
So go ahead, Rick.
I was just going to say, I don't know if you can see the chat box. There's a long list of questions in the chat box, some of which are also answered by other people in the chat box. One of the questions was, what's the difference between a salt dome and a salt cavern? And I understood you to say that there could be many caverns inside one dome. Is that correct?
Very good, Rick. That's exactly it. In Delta, Utah, there's one huge salt dome, and within it, a cavern is like the shape of a wine bottle, and there'll be up to 100 of these wine bottles within the dome, developed within the dome itself. So exactly right. A cavern is a subset of a dome. The dome is the geologic formation.
Let's see. One of the very first questions was asking you to talk about what the problems are with hydrogen storage. And of course, as hydrogen proponents, we all know there's never any problem with hydrogen.
Yeah, I think, you know, with a lot of these, I mean, we've seen some companies try to do above ground compressed air energy storage, and it just never pencils out because the amount of steel and material you need to store a meaningful amount of air just doesn't cover the value prop. And you know, the same with hydrogen. I mean, that's why we focused here on the very large hydrogen storage, because you really need to get that kind of scale in order to make the numbers work. Above ground hydrogen storage and trying to do energy arbitrage, that's just not a realistic kind of solution. So I think some of the issues with hydrogen have to do with restructuring the electric power sector in order to enable economic sopping up of these curtailed electrons, because that's sort of the next challenge, which is if you go in with a retail structure on electricity, you know, you're not going to produce hydrogen economically if you have to pay 18 cents a kilowatt hour or 12 cents for a commercial rate for kilowatt hour. So that's where some of the restructuring is going to be very meaningful for the green hydrogen gang.
The early in your presentation, Brad, you talked about seasonal storage as one of the measures of what we mean by long duration storage. And one of the questions is, how many hours or days or weeks or months are you shifting from, say, summer to winter? But I think it's important, and you can do the detail on this, but in these salt dome, these very large salt dome projects, it really isn't a seasonal shift. It's just an ongoing large scale shift, I think.
Yeah, in Europe, somebody is looking specifically at 2,200 hours and shifting specifically 2,200 hours from the high production part of the year, which is the summer, to the low production time of the year, which is winter. And so when we're looking at seasonal storage, you know, it's not cut and dry, as you say, Rick, you know, but there are people that are saying, we're going to need 22 hours of injection and 2,200 hours of injection and 2,200 hours of production. And the year has 8760 in terms of hours, and so that really is looking at about a 25% of the hours for production and 25% of the hours for injection.
Right. And you were talking about sharpening your pencil. One person asks, well, if you sharpen the pencil enough, are you apt to find out that it's cheaper to curtail the energy than it is to go through the hydrogen storage process?
Yeah, well, there are three parties at the table here. It's the people that put in the solar, the people that are doing the curtailment, and then the people that are looking at the opportunity to sop up the electricity. And we will talk about that in the transportation discussion next week, certainly, but it absolutely is critical. In other words, this is the opportunity. If you can get 2-cent power, 4-cent power even, and produce hydrogen for $2 a kilogram, that's marketable hydrogen. That's something you can take to the market all day long. And so I think that's what we're seeing here is that there's a third party that's coming to the table, and they're going to be looking at the arbitrage opportunity. If they can't prove out their business case, then indeed the questioner's statement would be correct, which is just leave it at curtailment. And that's where we are now. People are just getting curtailed, and they're actually getting kind of upset about it. And we can see this is why the wind companies in Europe are going direct to hydrogen, and then putting that hydrogen direct to steel manufacturing, or putting it in pipelines already. They're doing that on their own to avoid the curtailment deflation of the power cost opportunities.
Right. And they're also jumping ahead in the drive to get to net zero by 2050, which is a goal shared by lots of governments around the world, and governments and companies. The last 15 or 20%, or what's been seen as the last 15 or 20%, are those very difficult industries like cement and steel that will need a lot of hydrogen to produce heat. And by going wind directly to hydrogen, directly to plants like that, we may be solving the problem on the last 15% as part of the first 15%. Another question here, Brad, is not really directly on today's topic, but asking about the cost of shipping hydrogen, cost to ship a megawatt hour's worth of hydrogen as ammonia or as one of the other carriers. I'll let you address the numbers. I don't have them off the top of my head, but the questioner said, shipping from Saudi Arabia to the US as an example. And I wanted to mention that the Saudis are looking to pipe their hydrogen to the EU through long pipelines that they hope to develop. And that the shipping side of the aisle is in Australia, shipping to Japan, and Chile, anticipating shipping to both the Far East and to Europe. But I don't know if we have enough information on the costs yet to answer. Do you have cost numbers on that, Brad?
Not off the top of my head, but certainly, when you're shipping liquid hydrogen, it's fairly dense from an energy perspective. And so the cost of shipping is not very high because the ships are large. And the same with ammonia, that's already an established commodity that is shipped. And so I'm sure the cost actually pales in comparison to the underlying efficiencies of producing and then using the hydrogen fundamentally as well. And I think that's going to be the issue. I've looked at the cost to produce ammonia from hydrogen produced by renewable energy and find that it seems a little troubling to me, and I'm surprised people are so aggressively pursuing ammonia. But it bears further investigation. I think to be respectful of people's time, we have come to the end, and we are certainly, I'm open to receiving any additional questions you might have. I appreciate the strong interest in our hydrogen sessions, and we welcome your consideration in joining the Hydrogen Energy Center. Rick and Doug, your partnership on helping these sessions is invaluable. Is there anything else that we need to cover today in closing?
Just one quick housekeeping item. I know you're going to make the presentation available to everybody with a link. I don't know how to do this, but I'm pretty sure we can also capture the chat so that we can provide people with either a link to the chat or send them the chat so people will know what questions were asked. And it will also give us a chance to answer them on a personal basis to people who submitted them.
Excellent. Let's see if we can capture the chat before we sign off and lose it to the ether forever.
Right. It may just
So-
be a simple matter of copying and pasting it to something else.
Yep.
I'm not sure.
Somebody's mentioned that there's a save chat option, and we've just done that. So thank you for that advice. So thanks, everyone. We look forward to engaging with you on these important topics as we go forward. And again, Rick and Doug, thank you for your support in this modern age of webinars. Thanks, everyone.
Thank you, Brad.
Yep.